The derivative, you've come across this in school. So the first question, what is the definition of the derivative of a function y is equal to f of x? So you know from school, from first principles, f prime of x is equal to the limit as h tends to 0, and you're taking the limit of this expression, f of x plus h minus f of x all divided by h. Next question. What are the two important interpretations of f prime of x? Right, so one, f prime of x gives the gradient of the tangent to f at any point x f of x. So if you visualize this, supposing we got a curve which we're calling f, right? And if you take any point on the curve, then through that point you can draw a tangent to the curve, right? So this is the point x f of x. So tangent is a line that touches the curve at one point only. So if you take the gradient of the tangent line, then the general gradient is given by f prime of x. So f prime of x is really, it gives us the formula for the gradient at any point on a curve. The second interpretation, f prime of x gives the rate of change of f at x. Right. So the derivative can also be interpreted as the rate of change of the original function f at x, the input x. Let's look at an example. So first example, use 1.1, use the definition to find f prime of x. In other words, we need to work out f prime of x from first principles. So we are given what f of x is, the rule for f of x. So to organize the expression on which the limit is going to operate, we need f of x plus h. So that's x plus h all squared minus 6 into x plus h, squaring the binomial x squared plus 2xh plus h squared, using the distributive law, negative 6x minus 6h. So now organizing the numerator, f of x plus h minus f of x. Right, so what we have above, from above, x squared plus 2xh plus h squared minus 6x minus 6h minus your f of x now has two terms. You just don't write down x squared minus 6x. Right, you can see that there are two terms, so what we need is a bracket over here. And then we apply the distributive law. So simplifying, we've got x squared plus 2xh plus h squared minus 6x minus 6h minus x squared plus 6x. Right, so simplifying, you can see that the x squared minus x squared, that goes off. Then negative 6x plus 6x, so that goes off. So we are now left with 2xh plus h squared minus 6h. Right, and we can remove the h as a common factor. So it's 2x plus h minus 6. Therefore, f of x plus h minus f of x all over h will equal to, right, you can see the h will divide by the h in the denominator. So that gives us 2x plus h minus 6. So therefore, your f prime of x is equal to the limit as h approaches 0 of 2x plus h minus 6. And if you simplify, take the limit as h approaches 0, you get 2x minus 6. Right, moving on to page 2. 1.2, find the gradient of the tangent capital T to the graph of f at the point where x is equal to 1. Right, so what we want is the gradient of tangent capital T, the name of the tangent, to f at x is equal to 1, right? And that is given by the gradient of the tangent at x is equal to 1. It's good. The gradient will equal to f prime, the derivative of f evaluated at 1. So if you work that out, it's going to be 2 multiplied by 1 minus 6. So that's equal to negative 4. Now come to 1.3. Now determine the equation of the tangent capital T, right? Now, if you visualize what's happening over here, we know that f of x, the rule is x squared minus 6, right? So your f really is a parabola with the arms pointing upwards. And we are looking at x is where x is equal to negative 1. Right, we've got a tangent. We know that the gradient of the tangent is negative, so it has to be something like this. Right, so the gradient of the tangent is negative 4 from above. This point, the point of contact, it's 1, f of 1, since it lies on the original curve. So we've got f of x is equal to f of x is equal to x squared minus 6x. So f evaluated at 1, that's 1 squared minus 6 multiplied by 1, and that gives us negative 5, right, for f of f evaluated at 1. So the equation of the tangent, that's what we're trying to find, right? I'm going to take the y-intercept form of the equation of a straight line. So it's going to be y is equal to negative 4x plus, say, the y-intercept, which I can call k. So the gradient we know is negative 4 from 1.2. To find k, we need a point on the tangent, and that's the point of contact. So substituting the point 1, negative 5 gives, right, here y is negative 5. So y coordinate is equal to negative 4 multiplied by 1 plus k, which implies now that k is equal to -1. Right? Therefore, the equation of tangent t is y is equal to -4x minus 1. Right? Right. We now look at table 4 in the text. This is on page 369. Right, and this is applications involving a rate of change. So you got different columns. X, the input variable stands for. Y, the output variable stands for. Then we're looking at the expression f of x plus h minus f of x all divided by h, what it measures. And then we're looking at the limit as h approaches 0 of the expression f of x plus h minus f of a plus h minus f of f evaluated at a all divided by h, what that measures. So here in the second case, you can see you're taking the limit of the expression that's in the third column, right? So if x stands for time and y stands for the concentration of a drug in the bloodstream at time x, then the expression f evaluated at a plus h minus f of a all divided by h measures the average rate of change, right, in the concentration of the drug over the time interval, right, the closed interval from a to a plus h. If you take the limit as h approaches 0 of the expression, then it gives you the instantaneous rate of change at x is equal to a, right? So we move on to the next part. If if x stands for the number of items sold and y stands for the revenue at a sales level of x units, then the expression that heads the third column gives you the average rate of change in the revenue when the sales level is between x is equal to a and x is equal to a plus h. If you take the limit as h approaches 0, then that measures the instantaneous rate of change in the revenue when the sales level is A units. Right now, in the same way, you can go through the table and do the interpretations for when X represents time, Y represents volume of sales at time X. X, the input variable is time. The output is population at of fruit flies at time X. The input variable is temperature in a chemical reaction. The output variable is amount of product formed in the chemical reaction when the temperature is at X degrees. You need to go through the third and fourth columns and see each of the each of them measure, right? Uh, the expressions that are above the third and fourth columns. So we now go on to the next part, the next page, page 3, right? Example 2, let V of X represent the volume of sales at time X. What do the following represent? Right? The 2.1, this expression is going to give us the average rate of change of the volume of sales in the time interval, right? The closed interval from X to X plus H. 2.2, your V prime of X, in other words, the derivative of V as a function of X, this gives you the instantaneous rate of change of the volume of sales at time X, at that particular instant. Right, and then 2.3, the derivative of V evaluated at A. Again, this gives you the instantaneous rate of change of the volume of sales at time X is equal to A. Right? We now look at differentiability and continuity. Right? We dealt with the concept of continuity in the previous lecture. You'll find these concepts discussed on page 369. So the derivative exists when a function satisfies all of the following conditions at a point. One, right? So we wanted to satisfy all three conditions. The first condition is f is continuous. The second condition, f is smooth. In other words, there is no sharp part to the curve at A. And the third condition, f does not have a vertical tangent line. Right? That is for those three conditions must be satisfied for the derivative of a function to exist at a point. Now we look at from that the derivative does not exist when any of the following conditions are true for a function at a point. So one, f is discontinuous, right? So you need to know what's meant by discontinuous. That comes from the previous lecture. Number two, f has a sharp corner. Three, f has a vertical tangent line. So if you look at the third condition over here, in that case, if you take a vertical tangent line, the gradient is tan of 90 degrees, which is undefined. Right? This deals with the concept of angle of inclination. In other words, the angle made between the line and the positive x-axis. For a vertical line, that angle is 90 degrees. So we now move on to the next part. Right? You should note the following. Uh, if a function is differentiable, the point, it implies that it is continuous at that point. Right? And if capital A implies capital B, in other words, if some statement, capital A, which we're calling, implies the statement capital B, then not capital B, statement capital B implies not the statement capital A. This is a part of logic. So that is, if you look at above, differentiable implies continuous. So not continuous implies not differentiable. Right? So if we continue now to page 4, right? If a function is differentiable at x is equal to a, then it is continuous at x is equal to a. Right? You can look at what I wrote down in the previous page to understand that. Now, if you look at the graph of the function that's indicated in blue, right? You've got to the left of the y-axis at this value of x, you can see the function is not continuous at that value of x. So it follows that the function is not differentiable at that value of x. Now, if you look at this value of x, the input, you can see that the function is continuous, but there is a sharp turn. There's like an inverted V there, right? So although the function is still continuous, it is not differentiable. So let's look at the following example. Consider the graph of the function f. So it is a blue graph. Indicate whether f is continuous and or differentiable at these points, x sub 1, x sub 2, and so on, right up till x sub 6. Right? You'll see that on the graph that's drawn. I want you to attempt this, and then you can check your work against the PDF of the lecture.